In this video, we're going to talk about integrating rational functions, and that's polynomial divided by a polynomial. And to do integrals of rational functions, we have what's called the partial fraction decomposition, which can help us with those integrals. So the idea is sort of to undo fraction addition. So for example, here's an addition problem with two fractions, and you add together and you get this thing, one combined fraction. Partial fraction decomposition goes the other way. It starts with this fraction that has multiple things in the denominator, and it breaks it down as these individual factors or individual terms with simpler denominators. So if I wanted to integrate this rational function, then I could instead rewrite it as this sum, and I could just integrate these two simpler ones instead. And now, with a computer, of course, Sage will do the integral directly. We can just say integrate this thing and it's fine. So this is not really a how to use Sage to do something. Instead, I want to use Sage to do the partial fraction decompositions and see what kind of integrals we get. So we'll be more familiar with rational functions, what kind of integrals you get out of them. These can be very hard to do by hand. Just finding this decomposition is a chore by hand, and then integrating it. So that's what we're going to do. So here's an example of computing the partial fraction decomposition in Sage. First off, you define the function, give it a name. So I called my function f. And this is how the partial fraction command works. F of x, give the function name, then you put a period, and then you type out partial underscore fraction, and then parentheses afterwards. And there's a lot of commands in Sage where this whole put a dot after the input and then the name, it works that way for lots of different commands. This one, unless they change it, only works this way. Like you can't do, like normally a command in Sage you would do partial underscore fraction and then you put the f of x inside, and that's how you would do commands in Sage. But with partial fraction, for whatever reason, it doesn't work. I don't know what partial fraction is. So you have to do it this way with the sort of dot and then the name afterwards. Don't forget these parentheses at the end. That's also required. So anyway, that's a little bit strange, but that's what it looks like. So here's the partial fraction decomposition that comes out. Okay, so how are we going to use that? Let's say I want to find the antiderivative, or the indefinite integral, of this function. So I'm going to first off show you that you can't just integrate directly in Sage. So let's first define the function. Don't forget these parentheses around this bottom, around the denominator. So integrate that thing, and it gives me the answer. I have a logarithm piece. Remember, this is natural logarithm, ln. If I was going to write this down like I do down here, I would put ln. So I get these two different logarithm pieces. And so we want to do partial fractions and kind of see where do these logarithm pieces come from. Why is it these two different ones, these particular ones? Okay, so if I was going to write this out, first I would put ln for natural log rather than log. And also I would put absolute values here. Sage doesn't, but normally we write these absolute values inside. When you integrate, when you integrate 1 over x, the answer is the natural log of the absolute value of x plus c. And Sage also leaves off the plus c. So when you write that down, you should add it. Okay, let's do partial fractions. So here's the partial fraction decomposition. And now you can start to see where those two natural logs came from. This rational function involves two different factors in the denominator. There's an x plus 3 factor and there's an x plus 1 factor. And when you break them apart into partial fractions, you can integrate these separately. You integrate 1 over x plus 3 and you get the natural log of x plus 3, and you integrate 1 over x plus 1, you get the natural log of x plus 1, and then the 3 halves, the 1 half, those are just constants that are still there. Okay, so this is the partial fraction breakdown, so I'm going to integrate it and I get the natural log. So if you want to do it in Sage, integrate those two, you will see you get the same thing we got before. Okay, so that's an example of non-repeated linear factors in the denominator. So in general, if you have a rational function and the denominator factors into distinct linear factors, so all of these r sub i's are all different, and if the degree of the polynomial on top, so p here is the numerator, if that degree is smaller than n, so that's the degree of the denominator here is n, so degree is smaller on top, and you have n distinct roots on the bottom, then you always have this kind of partial fraction decomposition of that rational function. You get a term in this sum, one term for each of the roots, each factor, x minus r sub I, and there's some constant that will be up above. And those constants, doing this by hand, that's the hard part, figuring out what these a's are. And it depends on the function, and you can set up a system of equations and figure out what those a's are. You'll do that in the lecture. But here with the computer, we'll let the computer do it. Okay, so once you have this decomposition, then integrating it is not a big deal. So the constant just comes out, and you're integrating 1 over x minus r sub 1, x minus r sub 2, and so on. And that's just a shift of 1 over x. The integral of 1 over x is the natural log of the absolute value of x. This is just a little shift to the left or right. And so the integral is the same. It's just natural log of the absolute value of x minus whatever. And then you got your constant a's out front, and then plus c. Okay, so here's an example of that. I have 3 distinct linear factors in the denominator. So the degree on the bottom is 3, the degree on the top is 2, so the degree is bigger on the bottom, so I can have a partial fraction decomposition just like we saw up above. So define the function. Don't forget these parentheses around the top, parentheses around the bottom. Don't forget these explicit multiplications there, very important. You remember to put multiplications between the factors. If you leave those out, you're not necessarily going to get an error. Sage might do something unexpected. It won't give you the right answer though, but it might do something without an error. So make sure you have those multiplies there between those factors. Okay, first off, let's just integrate this directly in Sage, and we'll see we get three pieces of this answer, a logarithm for each of the factors in the denominator, just like we saw up above. So here's the partial fraction decomposition, and you can see now where those pieces came from, and where the constants came from. So this is what I'm going to have you do in your assignment. You're going to integrate it directly, just integral of the original f, and see what the total answer is. Then I'll have you do the partial fraction breakdown, and then I will ask you to integrate each one of the terms in this sum one by one. Okay, so I integrated this first, and you can just copy and paste from here, not from the showed version, but from this version. Copy, paste down here, integrate, copy, paste here, integrate, copy, paste here, integrate. Okay, so you'll see each of the 3 pieces of the integral come out of here. Okay. What happens if some of those factors are repeated? So if a root has multiplicity greater than 1 in the denominator. Well, that can happen. Let's start with a simple case when you just have one factor, or one distinct root with multiplicity n. So there's just x minus r is the only thing raised to the nth power. And again, we need the polynomial on top, the p here, to have a smaller degree, so a degree less than n. If that's your situation, then your partial fraction decomposition breaks down like this. You'll have some constant a, which that's the hard part, finding those a's. And what you get in the bottom is all the powers of x minus r. So you'll get some constant a over x minus r, and then another term will be a different a over x minus r squared, and so on up until x minus r to the n. Be aware also that some of these a's might be 0, so some of these terms might not appear, not necessarily. Okay, integrating these is also not that bad. Okay, we can take this, the constant, the a's come out of the integral. This first one, 1 over x minus r, that gives us a natural log. That's just like 1 over x here. Now these do not give us natural log. Okay, remember, natural log only comes when you integrate 1 over x or something, a shift of 1 over x. 1 over x squared is a power function that you can integrate using the power rule. Okay, remember, 1 over x is the only one where that power rule doesn't work, because the power rule for integrals says that you remember, add 1 to the exponent and divide by that new exponent. And if you start with 1 over x, that's the negative 1 power, and you would get division by 0, and that's why that doesn't work out there. And so that power rule doesn't apply when you have 1 over x. But any other power, it does just fine. Okay, so 1 over x to the n is x to the minus n, and the power rule says add 1, divide by that new power. And if you'd prefer to put it back down in the denominator, this is x to the negative n plus 1 is 1 over x to the n minus 1. Okay, so all of the first one here gives us the natural log. This one gives us that. And then 1 over x minus r cubed, you integrate that, you get this thing. And finally the last one, you integrate that and you get this one. Okay, so here's an example where we have a root of multiplicity 3 in the denominator. So here's the integral you get. You have a logarithm piece, and then you have this rational piece. Okay, notice up here that all of this, well, this is a logarithm, but from here on, these are all rational functions. And Sage adds them together and combines them. That's why we have just this one piece. Notice that I don't have, this isn't factored. So that's why I see it this way. Here's the partial fraction breakdown. Okay, I have 1 over x minus 1, and then I have an x minus 1 squared, and I have an x minus 1 cubed with various coefficients on top. I'm going to integrate each one of these. Okay, copy paste from the answer up here. Integrate each one individually. The first one gives me a logarithm. Second one gives me this rational function with, the power here goes down by 1 in the denominator. So x minus 1 squared becomes x minus 1, x minus 1 cubed, x minus 1 squared. Now, if I add these three things together, it doesn't look like exactly like that. That's because Sage has added these two pieces, added those fractions. Found a common denominator, which is x minus 1 squared. That's this, x minus 1 squared. And added those together. Okay? If you have more than one repeated linear factor, you just kind of extend that idea. So what we're going to get is you're integrated x plus 2 and an x plus 2 squared, and then you'll have an x minus 3 and an x minus 3 squared, an x minus 3 cubed, and x minus 3 to the fourth. You'll just have all those terms for each factor, and they'll all be added together in the partial fraction breakdown. So when you integrate, and again, watch out for parentheses and multiplies, you get a log piece for the x plus 2 factor, you get a log piece for the x minus 3 factor, and then the rest is rational. Let's see where all that comes from. Here's the partial fraction breakdown. And I have an x plus 2 factor, and I have x plus 2 squared, I get x minus 3 squared, x minus 3 to the fourth. Notice there is no x minus 3 cubed. That one had coefficient 0, the a sub whatever that would be, would give us 0. Okay, I'm going to integrate this thing term by term, and I got my two log pieces, and I have 3 rational pieces, and if I add those 3 rational pieces together, that would give me this big chunk here. Alright, now so far I've just had linear factors, and as you may be aware, not every single polynomial can be factored out into linear factors. Sometimes you have what's called irreducible quadratics. Irreducible quadratics have no real roots, so you can't factor them into linear factors, at least not involving real numbers. They actually, irreducible quadratics have 2 complex roots, which are complex conjugates of each other. So we don't want to deal with complex numbers. So any quadratic can be factored into a product of linear pieces and irreducible quadratic pieces. So once we've handled irreducible quadratics, that handles every rational function. Okay? Unfortunately, the partial fraction decomposition for irreducible quadratics is a little bit more complicated than for lines. So let's say we have a rational function that factors this way. So we got some polynomial on top. On the bottom, I have a product of distinct irreducible quadratics. Okay, none of these quadratics are the same here. Now all of these, if I have n quadratics, each of degree 2, then the degree on the bottom is 2n. I need the degree on top to be smaller than that. Okay, in that case, this is the partial fraction decomposition. You get a term in this decomposition, one term for each of these irreducible quadratic factors in the denominator. So there's the first one, and the second one, and so on. But on the top of this decomposition, you don't get a single constant like we had those A1, A2, A3 up above with linear. Instead, what you get on top is a line. So you have constant D and a constant E, but there's still an X here. So some sort of line over the quadratic. All right, now integrating this thing is oftentimes a pain in the neck. It's not quite so simple. Now sometimes you get lucky, and one of these might be a substitution problem. If you take the derivative of the bottom and you get the top, or at least a constant multiple of the top, then that's a fairly straightforward substitution problem, and the answer will give you a natural logarithm. If it doesn't work out that way, then you got to do some algebra. Usually there's some completing the square involved, and what comes out might be another natural logarithm, or it might be an arctangent, and it can be pretty lousy. So we'll be glad we got the computer to do this for us. You probably won't do a whole lot of these in class because they are a pain. So here is a rational function with two irreducible quadratic factors on the bottom. So degree 3 on top, degree 4 on the bottom, and here's the integral. All right, notice what we get when we integrate that. We have an arctangent piece, and we have two natural logarithm pieces. One natural logarithm piece for each of these irreducible quadratic factors. Notice those factors are what's inside the log. And then we have this arctangent piece. What's inside the arctangent is neither one of those factors. It's something else, 2x plus 1. So we'll do partial fractions and see where those came from. Here's the partial fraction breakdown. So I get one term for each of my irreducible quadratic factors, and on top is some sort of line. Integrating the first one is what gives us one of the logs and the arctangent. This second one gives us just a log. So let's see. Here's the integral of that first one, this part. Integrate that, and I get arctangent and log. And integrating the second one, this one, gives us just a logarithm. Okay, now why? This one here is the simple substitution. Okay, so I got x over x squared plus 1. The derivative of x squared plus 1 is 2x. That's a constant multiple of the numerator, the x. So substituting u equals x plus 1 gives us a simple substitution, and I get the natural log of the absolute value of u. And notice, since x squared plus 1 is positive, you can actually leave the absolute values off here. Now the other one is a little more complicated. So we want to integrate this guy. Now if we try to do the substitution of x squared plus x plus 2, and the derivative of that is 2x plus 1. And what we have on top is 2x minus 1. So the substitution doesn't work. We don't have the right thing. Now one way around this is to force the numerator to match. And we want, the derivative of the bottom is 2x plus 1, so let's just force a 2x plus 1 there. And of course, for these two sides to be equal, you got to add this little adjustment. Okay, 2x plus 1 minus 2 is 2x minus 1. So these are the same. This one is a simple substitution, because now the derivative of the bottom is exactly what's on top, and when you integrate that, you get this guy, natural log of x squared plus x plus 2. The hard part then is integrating this guy. This is not a simple substitution problem. This one, you need to, well, let's do it. Here it is. First, you got to complete the square in the denominator. Okay, so this happens to be how that square completes. All right, so I won't go through the algebra of completing the square. Then what you want to do is factor out this 7/4. Because what we want here, remember where you get arctan? Arctan is the integral of 1 over x squared plus 1. So what we want is variable squared plus 1. Now we got a little shift here. Shift is no big deal. Integral can handle a little shift like that. This is a shift left or right. But we really want x squared plus 1 here. And that is what gives us arctangent. So I'm going to factor out 7/4. And when I do that, I'll get whatever plus 1. Now factoring 7/4 out of this square is a pain in the neck. That's why we have a 2 over square root of 7 here. That's the 7/4 came out. Okay? And then just kind of put those together. I got this, so here's this fraction is the constant part coefficient. And then I got something with a variable squared plus 1. Now if we substitute this, we'll get 1 over u squared plus 1, and that's the arctangent of u. All right, so that's where that whole business came from. Now, Sage, where did Sage's answer go? It has factored some stuff out in here. I got the square root of 7 over 7, 2x plus 1 down here when I did it. So you have to fiddle around a little bit to get it to look exactly like what Sage gave me. But it is the same thing. And this is a whole lot easier than you doing it by hand. Now, in that example, I assumed that the quadratics, the irreducible quadratics in the denominator were distinct. If you have repeated irreducible quadratics, it's similar to what happens when you have repeated linear factors. So let's just start with one irreducible quadratic that shows up n times, and you get that factor with a line over it to the first power, and then that factor squared with a line on top, and so on. You get all these powers of that quadratic up to whatever this power is here to begin with. Okay, so let's try an example of that. So I got x squared plus 1, that's irreducible quadratic, and that's now squared. Here's the integral that Sage gives me. There's an arctan piece, there's a logarithm piece, and there's a rational piece. Where does that come from? Well, here's the partial fraction decomposition. I got two rational pieces. It's for each power of the x squared plus 1. Now this first one gives me this logarithm. That's a substitution, not too bad. In fact, I think it's the same one we had in the last problem. This one, well, not so simple. What does that one give me? That one gives me two pieces. Okay, if I integrate the second term, I get a rational piece and I get arctangent. Now I'm going to skip the gory details this time, and this is actually a trig substitution is involved here to get this arctangent and this rational part. I'll not go through that. All right, finally, in all the examples up above, the degree was larger on the bottom than on the top. What if it's not? Well, if it's not, then you need to rewrite your rational function using polynomial long division. So if I have a rational function that's p divided by q, where p and q are polynomials, and the degree of p is larger than or equal to the degree of q, then you can rewrite it this way. There's some other polynomials, I'll call them s and t. Those are the quotient and remainder when you do the long division. And the reason I didn't call them quotient and remainder is because I was already using r and q for rational and q for the polynomial, just because, I don't know, q comes after p. So that's why I didn't call them r and q for quotient and remainder. But that's what these s and t are. You do the polynomial long division, and this is the quotient s, and this is the remainder t. And when you do long division, the degree of t is smaller than the degree of q. That's how you know to stop the long division. Now, integrating the s part is simple. That's just a polynomial, so you're integrating those things forever. And integrating t over q is one of the examples that we did up above, because now the degree is smaller on top. But in Sage, you don't really have to worry about that. Okay, that's more if you're going to do it by hand. So in Sage, it'll handle the partial fraction decomposition in this case. So if you're going to do this by hand, first you do long division, and you'd find out you get this quotient, and this is the remainder is 11, and so it breaks down to this. And then you want to integrate that, you just integrate the polynomial the normal way, and then this gives you a natural log. Now there is a command in Sage that lets you find the quotient and remainder when you do long division. It's kind of cumbersome to use, and we don't really need it. You can search online if you really want to do it. But the partial fraction command actually will deal with this situation just fine. And so we'll do that. So here's the function. Here's the partial fraction decomposition. So you see the polynomial piece in this part. It's a little irritating here because the constant term they put at the end, they put all the variable terms first and then the constant at the end. I'd actually rather this plus 5 kind of go with this polynomial part, but anyway. So I'm going to integrate the whole polynomial part together. So I copied this, and then I went ahead and copied the 5 too. So feel free to do that on your assignment. The polynomial part you can integrate all at once, so we're not really worried about integrating polynomials. And then integrate whatever rational stuff you have left, integrate those one at a time. Okay, so there's the answer. And that's partial fractions.